So first, before I forget, the lunch vouchers. So everyone got some 5 lunch vouchers. Don't lose them. Put them in your wallet. They fit in the wallet for sure. They're very small. Do not lose them. And the way it works with a lunch voucher is we go to the restaurant, which is a buffet place. It's by the weight. And the voucher is worth 70 reais. So if you pay more than 70, you should pay the difference. 70 is enough if you are reasonable. So go there, eat normally. The first day you can calibrate a little bit if you can get more or less the second day. And that's it. So for those that were here in the Bootstrap, last time in the Bootstrap it was 65. So we upped 5 more to make sure you can get some extra fruits. Yes. So if at the end you realize you only spend 55 or 57 or 60, you can get some water or some dessert or some chocolates at the end to make sure you get close to as close to 70 as you might want. Very good. So that's about the vouchers. The key thing, put them in your wallet, don't lose them. Just on these logistic advices, just general things. So it's a huge city. Don't carry your phone around. Where am I going? Where is left? Where's the sun? Please. The phone, if you carry the phone around like this, especially in Paulista, especially at night, it's possible that a bike will pass and take the phone away for a ride. So just be reasonably street smart with the phone. So I think non-physics wise, that's it. So let me just say a few words about the conference now. So the goal of this conference is to bring together people that do integrability and people that do Bootstrap, so we can see what should we be computing, we that do integrability, what should we be computing that people from Bootstrap care, and what could we, inspired by results of the Bootstrap, what should we be looking at? We have this powerful technology to compute so many things. What exactly should we be computing and how the Bootstrap can help us and guide us and so on. And so for this format, we thought it made sense to have, if the goal is for the 2 communities to learn, to have lectures in the morning. So morning is mostly for learning. So we will have long lectures in the morning, and then the afternoon is very informal discussions. And so each afternoon has 1 discussion. 1 slot is still free, so if you have a topic you want to propose, do propose for Friday. Otherwise, we will have just a general summary discussion on Friday, spontaneously organized. But if you find a nice topic that we should discuss, please do suggest it for Friday. So in the mornings, we come here. In the afternoons, we come here for the discussion. And then we can use the building where we have the coffee breaks. So you will see it when we'll go for coffee break. And we can use any place there, especially the 0th floor and the 1st floor. They are the best places to discuss. But I will let you explore, and you will see there are whiteboards everywhere. There are discussion rooms. There are lots of sofas to sit and discuss on. There is even a rooftop that you can go and discuss there as well. So it's a very nice place just across. And so I said about the vouchers, I said about the conference, about just being mindful of the phone, and I think that's it. So it's a great pleasure. Let's start with the first set of lectures by Simon. Thanks, Simon. The topology is not like that.
Good morning, everyone. Can you hear me all right? Yeah, so like Pedro just said, this will be a workshop on integrability and Bootstrap, and that is why I will spend 3 lectures on perturbation theory. Because, well, it's good to talk about things start a workshop with things that are already known, and also it's neutral grounds. But I will speak specifically about like-ray operators. We're focusing on n equals 4 super-Yang-Mills, our favorite cast member in this integrability approach to field theories. And yeah, and so I would be saying things that are, yeah, let me just describe what they are. So there are basically two classes of like-ray operators. The natural class you can imagine are things that are localized on one like-ray, and the basic degree of freedom there, you insert a bunch of fields on a like-ray, and basic degree of freedom there is some like-cone position, like-cone coordinate at which you insert the fields. So these operators, roughly speaking, they describe the collinear limit, where you have many degrees of freedom propagating collinearly very fast in this direction. And there are other operators, so I will spend, actually most of the lectures will be about these types of guys. And in the end, I hope to say a few things about other things which involve many like rays, things like this, but now they go to infinity and minus infinity. And the interesting physics now is in the way that they are separated in the transverse plane. Okay? These are related to so-called Regge physics. Yeah. We talk about these two types of operators. From the viewpoint of integrability, these operators are controlled by a conformal symmetry of a like ray, which is a group known as SL2R. So this maps to a kind of SL2R spin chain. Okay, that's one way you could describe it. So I will describe its what I will describe is its at one loop in perturbation theory. What exactly is the Hamiltonian we want to study that controls these sort of operators? Its solution, and its solution I will describe it using integrability and the direct approach. So the solution, oops. So direct versus integrability. A lot of this will be based on on work by Kochimp. So yeah.
Let me pass the microphone.
Yeah. Thank you. Exactly. Yeah. These are infinite Wilson lines that go from past to future, but that's separated in transverse plane. Thank you. Great. Yeah. And here also there are Wilson lines separating these field insertions. Thank you. I will define the operator more precisely shortly. Not just kind of a schematic. This operator here will be controlled by SL2C symmetry instead of SL2R. But yeah, there's a series of paper by Derkachov. I'm probably not spelling it correctly. Korchemsky and Manashov, plus a variety of collaborators from 99 to I don't know, 2003, 2004, 5. They have a long series of paper where they explain this Hamiltonian, its solution, actually the solution using integrability. They describe the separation of variable approach to the wave function of this non-compact spin chain, which is quite a non-trivial story that is not very well known. So this will be sort of the main topics of these lectures. And well, as you may guess, we wanted to get Korchemsky to give these lectures. So I will not be able to describe everything in these papers, especially on the integrability side. However, the lectures 2 and 3 especially will be very hands-on. So I don't know exactly how to derive all the formulas in these papers, but I know how to implement them and solve them and show you some plots. So I will do that, and it will be very hands-on, and I will share this code. So that's the plan. But so yeah, we'll describe these objects in some of hands-on way. one of the broader motivation, I know, can you read? Maybe I would just write it here. So,
No, yeah, we can.
ah, that's smart. Okay. It's a modern lecture facility. Yeah. So yeah, well, some of the motivation is to, well, there are various motivations. So, well, first it's interesting to study non-local operators in using integrability. And one of the goals, for example, may be to understand in general, maybe this would give us some insight how to study correlation functions or amplitudes using integrability, and this sort of separation where we're still trying to understand how separation of variable works in the quantum spectral curve. So that could be a motivation for this. So it's an example of non-local operator. Oops. In integrability. And yeah, so the main goal really is that it could inspire some strategy. So we'll be discussing the one loop problem, but as we've seen in the past, once you've solved the one loop problem, then two loop and higher using the quantum spectral curve are kind of a perturbation of it. The hard part is to understand exactly how things are quantized at one loop. So that will be really why we focus on that. And so for today's lecture, I was planning to, so I guess I cannot erase this. So for today's lecture, I want to describe a bit of the historical situation where these operators of type 1 appear. So yeah. Where do 1 appear in physics? Describe some of the applications and how they connect to other things that you may know. Yeah, so any questions about the outline or wish list or things you would like to? So yeah, I will be somehow adaptable, so you can always discuss after the lecture if you want me to tweak the lecture in one direction or another. Yeah.
Just use the microphone because we are broadcasting live.
Yeah.
Yeah. So the light ray operators.
What type of light ray operator interpolates between integer spin operators on a double twist trajectory in a CFT?
Yeah, exactly. That's the sort of things we want to answer. So these operators, they will have continuous spin in general. And when you localize them to integer spin, they happen to be local operators. But in general, they interpolate between integer spin. And the sort of ideas we use here would be related to things that you would use to study double twist operators. But these operators here would be all single trace operator in this theory. Okay? So we'll be focusing on single trace operators, but the dynamics is probably similar to double twist operators in general CFTs. Yeah.
Okay.
How well is interpolation between 1 and 2 understood? I mean, at the level of diagrams.
The beautiful thing, that they showed is that here the physics you have a like ray, here the physics you have a transverse plane, but they shown that the problem is in some sense is double copy of this one. So they say that here in integrability the star of the problem are these Q functions, which are a function of U. And here you have functions of Q and U bar, where U bar minus U is I times an integer. So you have this kind of slightly more generalized Q function, but they still satisfy independent Baxter equation and so on. So you end up being able to write them as a product of Q function like this. So, and then they have some quantization condition for this problem and so on. So once you solve this problem, there's a way to go into this problem according to them.
Yeah, so Well, my question is how general is this passage known from 1 to 2? Like if you solved 1, can you always figure out what's going on in 2?
No. Very important open question.
Yeah, I just want to make a trivial comment that in principle, these types of operators, they can mix in special cases, right? So they're not like super distinct from each other in a way as well.
Yes, that is true. Especially, yeah, one basic picture actually, as you know very well, Kolya, is that okay, now I'm going a bit in advance of the talk, but if you plot the spectrum of this operator, delta minus 2, j, these like operators, they live on some trajectories that are close to 45 degrees. And okay, sorry, let me do a proper plot. This leading trajectory, then there's a bunch of subleading ones. That's somehow the spectrum that you have. And as you know, when you go to low spins and low scaling dimension, there's a mix with the other one. So this will be the collinear guys here, and this will be the Regge guys horizontally. Yeah. So they kind of talk to each other when you go to these extreme values of low spin. Yeah. So they do talk to each other in these ways. Yeah. Indeed.
Are you choosing a specific way to continue the spin, or is general?
In generic weight, so the overall spin of the operator is a continuous parameter in this plot.
I guess he's asking whether, like, given a spectrum of local operators, whether you believe there is the only like best way to analytically continue.
Yeah, because in principle there could be many different trajectories.
Yeah, that's a good question. Yeah, it's indeed some people have studied. Suppose you know only the spectrum at integer spin. How do you draw a line that passes through all the points? To continue it, this is not the strategy we'll come in. So as I will explain today, in the way that these operators show up, these non-local operators show up in the physical situation where they show up, they naturally have a Hamiltonian which is defined for an integer spin. So you can try to directly solve this Hamiltonian. So the problem starts with non-integer spin already. Okay. Yeah, that would be the main point of today's lecture. So let's review a bit where these operators first appear historically. The first place where they really appear in science is a Parton distribution function. Okay. Okay, here we'll have to step away temporarily and talk a little bit about collider physics, because that's the origin of this subject. After all this, we're related to particle physics. So the general idea there is that you study scattering of 2 protons at very high energy. The main thing that will happen, so this proton is made of a bunch of quarks and gluons. And the main thing that will happen as you scatter them at high energy, and if you ask, what's the probability that you get a jet of stuff in a transverse direction, that will be controlled mainly by having one object from one proton hit almost head-on with an object in the other one, and then they deflect here. Okay. And if you're studying a jet which has an energy, let's call it q perp, some momentum q perp flying in the other direction, the typical scale that you're probing here are 1 over q perp. Okay, so mostly, what happens when you do PP collision and try to explain what comes out at wide angle, it's a bit like the classic Rutherford gold plate experiment. Mostly, things miss each other and go straight, but sometimes 2 so-called partons hit each other head-on and scatter 90 degrees. Okay? This is what gives you actual signal. And so, for example, if you want to know the probability of producing Higgs in the standard model and a PP collision, this scale q perp will be the mass of the Higgs. And so your two partons would have to be very close to each other to probe that. Okay. And once they've kicked out, they eventually shower and do a sort of complicated thing. But the time scale for this showering is very long, because this is a highly boosted object. So there's a time dilation factor. This time goes like lambda q perp over lambda qcd square. So all this whole complicated physics is happening ages after this basic process is happening. So as far as hard physics is concerned at LHC collision, the only thing you really need to know about the proton is what's the probability to find a quark with a given energy inside the proton. And that's what these distribution functions answer. Okay, so this PDF. So there's some function, say, of some variable x. It's equal to the probability of finding a quark with like cone momentum p plus is equal to x times total p plus of the proton. So you have a momentum fraction x, where x naturally is between 0 and 1. Okay? So the idea is that you have this proton is accelerated very fast, and we're picking an object here that has a momentum xp, x times the momentum of the total object. Okay? So the answer to this question is related to light-ray operators. This connection was explained rather clearly in a paper by Collins and Soper in '82. So the title of the paper is Parton distribution function and decay functions. And I will just follow a little bit the introduction of this paper to tell you the idea. The idea is that what you want to do is you want to take something like a proton. It's going to be an expectation value in the proton state. It's a probability, so it's an expectation value. And you want to write down something like a number operator that measure probability of proton. So here we're going to start with the free theory and then generalize this. Okay? Just to motivate the concept. So in the free theory, you try down to write something like this. And this A here, you want to put a momentum that is that has x p plus and the given p perp. And the transverse momentum of the things you scatter, they're very small. They're order lambda QCD typically, so they almost don't matter. So you basically want to integrate over that. Okay. So that's the thing that we want. We want to measure a number, expectation value of some number operator that measures number of, say, quarks, which have a given energy, but any transverse momentum. So we integrate over that. Okay. The fact that we're integrating over x perp, so over p perp, means that essentially, when you go, and the other thing we could use is if you use free field. I'm not going to write this formula explicitly, but if you have a quark, you will write it as an integral over p of some wave function plus u bar a. So you will insert the mode decomposition in the field. You can relate this to field operator. So this will be some matrix element of that's bilinear in the quark field. And the fact that it's integrated over p perp, you can do a Fourier transform, and you will integrate over x perp. And the fact that you're fixing the energy of the thing you measure means that you have to do a Fourier transform. I'll put dy minus dz minus. Let me put this. Let me call this y perp because I have too many x's. Okay. And because you want the total moment, you want to these two things have the same momentum, so you will insert them at the same transverse position. Z minus y perp. And to extract the wave function that you want for high energy fast particle, I'm going to put a gamma matrix here. And that's basically what we want. And we have to do a Fourier transform. So there's a Fourier phase, exp of I xp plus y minus z minus. So you have to do a Fourier transform of this thing. So you see this like ray operator appearing here. They're on the same like ray. The two things on the same like ray because you want to integrate over all transverse momentum. Okay, that's the reason. Okay. So in a full gauge, of course, this operator that I wrote is not gauge invariant because the two operators are separated in this minus direction. But you make it gauge invariant by adding a Wilson line. So we have a x minus, y minus. By inserting null Wilson line from x minus to y minus. And for quarks, that will be a fundamental Wilson line, okay, to make the object gauge invariant. We put W here. Yeah.
A bit silly question.
Great.
So, well, I mean, in QCD, obviously, you can only insert Wilson line, but in N equal 4, you can insert lots of different type of Wilson lines. How do you know which one is the best?
So in N equals 4?
If you insert like half BPS version of Wilson line, for
yes.
example.
Yeah, so for the version that I will talk about, I will be inserting fundamental Wilson lines and connecting the adjoint fields in a way like this. That's a definition of the things we'll study. One thing to notice is that these operators commute with each other. So if you put a fundamental Wilson line and anti-fundamental here, this you could also say it's like having the adjoint Wilson line. There really is no difference. Well, the air depends how you connect it, but if you put the suitable group theory tensor here in the middle, this is having pair of fundamental Wilson line is the same as having adjoint one here. Wilson line does that, right? So the question really is what invariant tensors you put at these vertices. I will sidestep this question by focusing on the planar limit, where it is really just kind of like one option. Everything has to organize into one trace like that. But away from the planar limit, you're right, there is a question of what invariant tensors you put from the gauge symmetry at each of these places. Yeah. For the Parton distribution functions, this question is answered because you want the object to be overall gauge invariant. It's a probability. So it's what the representation of Wilson line is determined by the representation of the partons you're inserting.
So we notice you answered slightly different questions. So my question was, why can't you insert half BPS Wilson line instead of pure?
Oh, I see what you mean. Turn on a scalar. Yeah, because these are null Wilson lines, it doesn't matter. So I think what Corey is asking is about this thing in gauge theory. We can put the usual Wilson line will have something like this. Then you can add some integral of phi times dx, something like this. But this is 0 for null Wilson line. So there's no decoration you can turn on here. Thanks for the question. Okay. Yeah, I know you like these objects, but well, you could say that I'm studying these objects. They just happen to be normal Wilson lines. Okay. And the large boost limit, they become errors. Yeah. Okay. Okay. Questions. Okay. Yeah. Let me make a few comments. Yeah. And yeah, in some situation, this is not only natural but also correct. There are long discussions in literature about when this is actually correct. To just connect this by Wilson lines, it requires that you're sufficiently inclusive with respect to final states. But I won't go into this here. But yeah, so that's the definition. So you just do a Fourier transform of this bilocal operator on a like tree. That gives you the probability, you sandwich that in the proton state, gives you the probability of finding a quark, a parton with that momentum. So here's a few comments. So, okay, a first sort of trivial observation is just to get the kinematic straight. If your proton is moving in the x plus direction, your like-Fourier operator is actually probing it, and it has to be going like the probe that's probing it, so it goes in the minus direction. Okay, so like if proton moves along x plus, then probe operator is along x minus. Right? It's roughly speaking represents the thing that you're hitting the proton with to probe it. That's just a basic kinematical thing to get straight. Another simple statement we can make is that if we take moments of this object, we reduce to local operators. Partial integer moments reduce to more familiar local operators. And that's very easy to see. So what's the integer moment? So basically, if you integrate from -1 to 1 of dx, I will label the moment by a power of j minus 1 of this bilocal operator times the Fourier transform. Let me just call it f, sorry. X. So the integral from -1 to 1 is the same as the integral from -infinity to infinity, because this distribution vanish. You cannot absorb a parton which has more energy than the proton you start with. So, and if you compute the integral over this momentum fraction here times an integer power, basically this will turn into a delta function or a derivative of a delta function that sets these 2 points to be equal. So you get integral from dy minus of psi bar, gamma minus, and then you get derivative of the j minus 1's derivative of this thing. Okay, so that's a local operator. Okay, so this connection is so it's clear. Yeah. So if you look historically, Parton distribution functions were initially defined in 1971 or 72. It's actually in the paper by Gross and Wilczek where they talk about the symplectic freedom. They define Parton distribution function, and in this context, what they really defined were the moments of the Parton distribution functions from these local operators. But if you look at these things and wanted to make a generating function of these things, you will naturally write down this sort of object. So you can think of this just as a generating function of all these moments. However, this Parton distribution function is defined more generally than the moments. Okay. But yeah, a lot of textbooks like Peskin and Schroeder, they emphasize this connection with the local operators. Another thing that's important about these operators are the quantum numbers. So the physical motivation of this Parton distribution function is to imagine a process where we have a large transverse momentum so that you're only going to see one parton from each object, each proton, and all the rest will just fly straight. The large parameter which controls this limit is Q_perp. Okay? So the scaling at large Q is controlled by a certain quantum number. It's controlled by a symmetry, which is basically the transverse dilation of the object. Controlled by the transverse dilation. Because we're interested in the scaling where Q is very small. Sorry, 1 over Q is a small distance. But the energy is fixed. So you're fixing the energy that you absorb, but you're looking at very short transverse distances. So this transverse dilation is basically the usual dilation operator But if you apply a dilation operator, you also increase the longitudinal energy. So you can restore it back by subtracting a boost in the plus-minus direction, see, and the boost along your beam axis. So this object, the eigenvalues of this object, is a dimension minus spin, known as a twist. Okay. So the particular operators that I wrote here has a scaling dimension, so each psi in the free theory, each psi has dimension 3/2, so this is dimension 3 plus j minus 1, that's 2 plus j. So this operator has twist equal 2 plus loop correction when you look in the free, at weak coupling, okay, for the leading ones. And this 2 makes a lot of sense when you think about it, because what this operator means in this formula is that it represents a density of Parton in the transverse plane. It's only after you integrate over the transverse position that you get a number. So this is the right number for a transverse density of Parton. Okay? So the twist gives you how things behave with respect to a rescaling of the transverse plane. And 2 is the magic number that gives you a density. Okay? But the quantum correction means that if you look a bit closer, you realize that it's slightly harder to find a Parton than you would think. Another comment related to this scaling is that it's also clear why, if I replace this gamma matrix here by another index, so if I use gamma perp or gamma plus, this would give you higher twist effects. So that would give, so replacing gamma minus by gamma plus, gamma perp or gamma plus would give an effect that is suppressed by basically lambda QCD over Q effect. Okay, the so-called higher twist effect, which are almost always neglected. Okay. And maybe a last comment. So we talk about the. So am I doing on time? Okay, that's great. I have like 20 minutes left. Something, is that the idea? A bit more. Yeah, good. Great. Okay. So the comment is that, so this anomalous dimension here, they give you the so-called Diglap evolution equation, or Parton evolution. And in QCD, it's known to 3 loops. Well, almost finished. It's partially known to 4 loops. It's almost done to 4 loops. So people really do precision physics with these things. The thing which is hard is the fact that F is a matrix element of this operator inside the proton, and the thing which is hard is the proton. It's a hard non-perturbative object. So yeah, what's hard is the proton. What's difficult is the proton. UCD is the proton. And this, we don't really have a good way to calculate this. So because of this, we know how these things evolve within the resolution, but we don't know how to calculate this from first principle. So basically, these things are measured. Fundamentally, these things are measured. So the Fs are determined by measurements. And then evolve and scaled. Okay. Yeah. So if you ask a QCD person, in terms of the, or so more generally in terms of the physics program at LHC for discovering new physics, these Parton distribution functions are really an important aspect. So if you ask a person doing this sort of physics, what would it mean to solve QCD for them? Well, it means being able to calculate this from first principle. If you could do that, that for many purposes, this is what it would mean to have solved QCD.
Can people compute them on a lattice?
Yeah, so there's some measurements of the first few moments. The low moments are amenable to the lattice. On lattice, you can only measure local operators. But it becomes very hard to measure the higher moments because these are very high dimension operators. You don't have natural like cone derivative on the lattice. You only have derivative in usual directions. And it's very tricky to organize operators in because you're breaking rotational symmetry. You have to organize them. The other thing that's tricky is that what matters most is the normalization of these things. So you have to make sure you use the correctly normalized operators, which is tricky. So I think it's very challenging on the lattice. People are working on this, but it's hard. I don't know if anyone knows more about this, but I think that's a fair assessment of. So let me now describe the thing that we can calculate in perturbation theory in QCD, and that's also this Hamiltonian we describe, that describes the Q evolution of these objects. So I will say a few general words and then describe them explicitly in n equals 4 Sprague angles. Okay. In n equals 4 Sprague angles, you don't have the analog of a proton to take the matrix element in, but you can still talk about this operator, and you could imagine taking this matrix element in pretty much any state you want. Okay? We're interested about the physics of these operators. Okay. So the rough picture is that if you imagine a process where this, like with this Parton contribute, so imagine you have some scattering in the picture that is there. You have some R matrix elements, stuff come out. Sorry. Let me just abbreviate this as dot 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 on the right. So a scattering cross-section will be proportional to some matrix element square that looks like this. And the first thing that would correct this is that you can have a radiative correction. So you could, for example, radiate a gluon here. So if you started with, let's call this blob M. So if you started with an object that had momentum xp, and you radiate something, let's imagine you have let's imagine that this relation is collinear. Then effectively, this thing here will have a smaller momentum, still collinear, but some momentum fraction xpz. So collinear radiation replace m of xp by m of z xp. Okay. So if you radiate some fraction of your momentum away, then what you're left with to scatter is a smaller fraction. Okay. That means that, so effectively, the probability that you observe this Parton here with some momentum fraction is related to the probability that you had a higher energy before you radiate. So what this means is that this f of x mixes with f of x prime with x prime greater than x. Okay? So these operators with different momentum fraction, they all mix with each other under renormalization. Okay? And people write down the RG equation will look something, so there's a resolution scale associated to this. Let's call it mu. Well, it's related to q. Let's call it q. The usual RG equation that looks like q dq plus beta of g, the beta function, d over dg, fi of x at the scale q, is some integral from z over z, x to 1, p of z, f of q, x over z. So this RG, something that's known as RG equation, and this p here represents the probability that you observe something that you split such that you observe something that has momentum fraction z of the original thing. Okay. Okay. So there's this thing. This probability can be relatively easily calculated. I will not describe the calculation here, but if you do something like this in say, for a scalar, a complex scalar, and then of course for square MGills, basically what you will need is this blob here, and tacking this blob on the diagram, if this momentum k looks like this, and you're radiating a gluon with polarization epsilon, you get something like g times epsilon perp dot k perp over k perp square. So this is the splitting function. And yeah, I think I will, using this splitting amplitude, which is basically a 3-point vertex times a propagator, you integrate this. So I will not reproduce this calculation. It's actually nicely done in textbooks like Peskin. You get this p, which is related to that. And now I will describe specifically what you get for scalar. So a specific example. So they are the simplest of these twist 2 operators you can consider. Would be something like let me write down various things. So the simplest family of operators you could start with is you could write down a complex scalar z, and you can try to make sense of derivative to the power j. And in general, for j non-integer, you can write this naturally as, let me put sorry, I'm supposed to. I'm doing a bit of a jump here, so I'm defining the likelihood operators that we'll actually study in QCD, that are, sorry, in N course 4, that are a generalization of those I wrote in QCD. They are this type of objects. I'm integrating over y minus to project into conformal primary, so I don't have to worry about which place this derivative act. And this thing here, projecting into spin j, is the same as basically integrating against y minus minus z minus times minus 1 minus j times trace of z at x minus z of, sorry, y minus z minus. Yeah, and there's some Wilson lines connecting them that I'm omitting. Yeah. So that's the operator. The basic ingredient here is something I would call O of yz. So it's a product of two scalar fields that sits on the same like ray, but 2 different times. And if you integrate against that, you get this operator, which is basically something like the jth moment of the distribution function of this z. Okay. Okay. The fact that this operator mix, the thing that measures some energy mixes with something that measures a different energy, means that if you look at this basic building block, which depends on the distance, means that operators of different size mix with each other. Okay. I erased the Wi-Fi. This is bad. Oops. So maybe let's write it in two coordinates. So this, in momentum space, the evolution of this operator, so this thing is what I call the Hamiltonian. That's the thing which gives the twist minus quantum corrections of this operator. This Hamiltonian in momentum space looks something like this. Integral, sorry, this is momentum function x. I think it's, let me try a different black marker. So it's the thing I just wrote. And in this particular case of n-cross 4 Spring-Yang-Mills, this can be calculated from, as I said, the matrix element of emitting a gluon. And it gives you the following. You can write it as integral d alpha over alpha of f of x minus f of x times 1 minus alpha times 2g square n. Sorry, it's a eight g square n. Sorry. That's this object. So this is the thing that comes out of a this diagram calculation.
Is there any alpha dependence in the first term? So is it f of x or f of alpha x or something like that?
Yeah, so the first term here is just at x. Yeah. So this is coming from essentially virtual correction. So in terms of the operator, when you calculate the cross-section, you calculate m times m star. There's a contribution where you emit a gluon and do something like this. And here you start with x, and here you have x minus, so you have momentum p here. Here you have p times 1 minus alpha, and here you have p alpha. And there's also a virtual graph that looks like this. And this virtual graph gives you the same p here, so that's this term. So these two terms nicely combine. They have to combine with exactly this combination, such that total number is unchanged. It does not evolve in this process. Okay. So this diagram gives these Hamiltonian. And this is restricted to 0 total momentum, but you can write a similar Hamiltonian for the general object that has that is a function of 2 times. And so if I take this operator, which is a function of y and z.
Sorry, Simon, very basic question. So that propagator there, after you emit the particle, is it on shell or off shell?
It's off shell, but it's almost on shell. This one is almost on shell because this is collinear.
So why isn't it on shell?
Yeah, this is on shell on the outside.
Yeah.
So this one, sorry, here you have some blob that represent the scattering process that happens. So here it's hitting something, and like in this thing here. This blob in the middle is this process here. Whatever your proton that's coming from infinity is hitting.
But
So
that
so
red
this
propagator, isn't it on shell?
No, it's off shell. It's nearly on shell because the radiation is collinear. And if you start with something on shell and you emit something on shell that's almost in the same direction, you're still almost on shell.
Okay.
And the fact that you're almost on shell is why you get this large this almost 1/0 denominator in the collinear direction. But this is not on shell. Same here. So the analog of this in position space has a simple form that is 4g square n. Sorry, and is the 4 pi square. Sorry. So let me just write it as lambda or 4 pi square. So this is the thing that in integrability people just call g square. And this integral 0 to 1 d alpha over alpha O of yz minus O of y prime comma z minus O of y comma z prime. So what's going on in position space, if you start with an operator at z and y, and you apply this evolution, it mixes with shorter operators. So there's a term in which this guy A endpoint moves to a point y prime, and y prime is a point between y and z. So y prime is basically y plus alpha z minus y. So there's a term where so you can make the operator shorter either by moving one endpoint or by moving the other endpoint. So that's what happens in this Hamiltonian at. So that's the one loop Hamiltonian of these objects. Okay.
Can you comment a little bit on the precise derivation of the formula in the first line? I'm just a bit, my confusion is the following. So I'm used to seeing this Hamiltonian from a different direction, where I come from renormalizing local operators.
Yeah.
But this looks much simpler. So the diagrams that you drew look like some trivial diagrams where I either remove or not. So
yeah. So they
is it really precise, or it's
it's precise. So the one way you could think about it is so if you start with this object and you compute its matrix element in some unshelled state with two scalars. Okay. Here you're emitting this scalar. So you have to have some propagator connecting to them. And sorry, I'm saying it wrongly. Yeah, it's not entirely obvious. It turns out that the diagram which gives you the divergence is a diagram that looks like this, where one scalar stays at the same point, and this thing here, you get the divergence when this vertex approach this light ray, because then all these distances are null. And this divergence here give you effectively like you were sourcing the scalar somewhere along this line. So divergence mostly comes from this diagram, and it's permuted one, which gives you the other term. At higher loop orders, both points move. So the fact that one point was fixed and the other move is a very one loop artifact, not generic.
Sorry, but I think this picture is kind of more familiar. So that's the way I extract log divergences to learn about the Hamiltonian.
Yeah.
But in the previous picture, you were not mentioning log divergences or anything. You were just cutting some diagram in the middle and drawing things from left to right.
Yeah. So when you integrate over this, let's call this momentum k. When you integrate over the momentum of this guy here, you end up with a 1 over k perp square from this propagator. And this gives you the divergence. And you're interested in partons that have inner momentum up to q. So this has a log q in it. So it's the same. You extract the coefficient of a log divergence in this diagram. This diagram has a log divergence. But it's a momentum. So this is a coordinate space calculation. This is the momentum space calculation.
Am I supposed to look at the two diagrams and see that they are similar or the same? They look totally different to me.
Yeah, it's a good question. It's not completely obvious why they match. Yeah. Sorry, I'm not. We can discuss more after, but I'm not saying the match between. Roughly speaking, I think what you're supposed to do is in this picture, this direction is x plus. So I think you're supposed to take this diagram and stretch it in this direction, and now you will have this thing here radiating a gluon that hits the other one. But yeah.
But the point is to derive the first line, I don't use the bottom graph. I use the top graph, right?
Yeah, okay.
The bottom graph, I think I know how to derive the bottom graph from a different approach, from the usual Hamiltonian, right, of normalizing the operators.
Yeah.
But you are saying there is a faster way of getting to this expression where I just draw those virtual gluon exchanges, and either they pass some dashed line or not, and immediately they give me the two terms.
Yeah. Yeah, it's kind of cool that these give you the same answer. But I don't think I can explain why. I'm a bit. I don't see it immediately, so I don't think I can explain it now. But we can discuss later. Yeah. But yeah, it's a neat fact that there's a lot of different ways of computing these numerous dimensions.
Perhaps if you put the operator in future null infinity, then.
Sorry.
Perhaps if you put the operator in future null infinity, that's one of the. Maybe that's how the relation goes.
Yeah, I think what. Yeah, the related calculation that Peter is mentioning, which is not exactly the one I was describing, but it's this one here. It's not this one I was doing, but yeah. If you take this operator here, and you insert it at cry plus, then the calculation of the matrix element of this operator becomes literally this diagram. Then the gluon crossing the cut is the gluon that's radiated before hitting cry plus. So you're right, yeah. So there's a nice map between this calculation by inserting these operators at infinity on cry plus. Okay, so that's the Hamiltonian. That comes out for these functions of positions. And okay, let me say a few things. So this thing naturally generalizes to. So we have two operators. You can naturally define operators with 3 points on the like rays, and this generalize. So this generalization was written down by Brodsky Lepage in '81, before the So if you have more points, there's an evolution equation. So you have something like O of x, y, z, ... So you have 3 points. And yeah, we'll just write it in the planar limit, where it is a very simple form. So if I take this trace of 3 operators, in the planar limit, we have 3 points, x, y, z. It's simply a sum of pairwise interaction. So there's a term where z slides toward y, the term where z slides toward x, the term where y slides toward z, and so on. So basically, you have a sum of all the possible pairwise permutation of this thing. Okay. So let me call this thing object here h, y, z. Sorry, that's 2 h, y, z. Yeah. So I put a 2 here and a 1 here, just to get the numbers right. Yeah. So basically, you get h, x, y, plus h, y, z, plus h, z, x, acting on O.
So could so is there some ordering of this coordinates x, y, z? Do you normally assume ordering or not?
Yeah, this would come in when we diagonalize this object directly. So when you have 3 objects, they can actually be order, and the time ordering can be different from the ordering along the trace. So in fact, for 3 operators, you can always assume that it either looks like this, or it looks like this. For 3 operators, they always only look in one of these cases. These cases are related by C symmetry. And because C commutes with Hamiltonian, you don't actually... yeah, for 3, there's just that number. For higher points, it becomes more interesting. We can discuss this after. But for higher points, you have operators where things are nicely ordered. But you can also imagine operators where things do some zigzag along the trace. And these will never mix to produce that. That's kind of a cool thing. But this can produce that, but not the other way around. So it's not entirely clear how to understand all of these enormous dimensions. But we'll be discussing this case in detail in the next lecture. Yeah. thanks for the question. But yeah, the Hamiltonian itself can be derived in all the cases. So there's a formula like this. So that's a well-defined Hamiltonian. It exists for any, well, it doesn't even refer to spin, so we can try to, it commutes with spin, so we can diagonalize spin and study the eigenvalues of this Hamiltonian. Maybe I would just say a few things about where these operators show up. So some of the historical motivations for these objects. So one of the sort of obvious situations where they come in is multiple Parton scattering.
Sorry, can I let me just ask a related question to what Collier was asking. So this Wilson line, you connected z and x. You could also make an infinite line going from z to plus infinity and from x to minus infinity.
Yeah.
Is it the same? Is it different?
Well, depends. If you put a spectator charge at infinity, if you don't put any charge at infinity, the Wilson line will have to go back, and then it's like you have nothing. But if you put a spectator charge at infinity, then yes, you can be dragged towards it. That's like, so this, yeah, we're not discussing this case, but here I'm talking about like a closed chain, but you could imagine something like an open chain where you put some spectators to infinity, and the spectators cannot move. You could imagine things like that, yeah.
This term Hamiltonian, say, let me think which one I want. Say the last term, zx.
Yeah.
Will it move the x towards the z passing by the y, or will it stop when it hits the y?
No, it passes through.
And then when it passes through, it does not develop these zigzags, but instead it goes from the picture on the left to the picture on the right.
Exactly. Yeah.
But if it was 4 points, then you would develop some zigzags.
Yeah, in 4 points you have more things to think about, like yeah, things like that. Yeah. Not necessarily zigzags, but you have other options. Yeah. Yeah.
This is invariant of the conformal transformations.
Yes. So this Hamiltonian has has interesting symmetry. So it has SL2R symmetries, which are the conformal symmetries of a like ray. So, right, obviously it's translation invariant, it's scale invariant, but it's also invariant under conformal transformation. One other thing which is amazing about this Hamiltonian is that when you Fourier transform it, it looks the same. So it also has the dual conformal invariance. So these together give you an infinite set of quantities, so it's integrable Hamiltonian. So yeah, this Hamiltonian is integrable, which is why we'd be able to analyze it. Yeah, it's actually it is the so-called Heisenberg spin chain for the SL2R symmetry.
So in principle, we are like 5 minutes away from the break. So
Okay.
I don't know if you want to.
Okay, maybe I'll just say just a few quick thoughts about the content. I'll just draw a few pictures. So where this appears. So one place is. One obvious thing is that if you imagine, so we said that the main thing that happens when you scatter proton is that you see one quark from or one parton from each. But one thing you will have is you could have a small correction, small terms where two partons are on top of each other and not on the other. So that would be a twist 3. So this is a term with two partons here and one parton here. So it's interference, yeah. And this interference term would be suppressed by lambda QCD over Q compared with the other terms. Okay. That's one place this happens. It's not studied a lot. I mean, people have estimated this thing, but essentially usually smaller than other uncertainties that we have. So it's not a big, doing this thing precisely is not a big focus. Something else where this twist operators show up is when you do exclusive scattering. This is really old school, But for example, if you study proton pion goes to proton pion plus nothing. Okay, that's what exclusive scattering means. That's what a scattering amplitude means. So the pion is made of two quarks. And suppose you want to do this at large angle scattering. Sorry, that's supposed to be 3 lines, 2 lines, 3 lines. There's this thing called the Brodsky-Farrar counting rule, that the scattering amplitude would go like q to the 4 minus the sum of the twist. So that's the minimal twist operator which creates hadron I. And the physics of what happens here is that you have an object. In order to do this hard scattering with a large momentum transfer Q, you need essentially the whole object, each of the pion and the proton, to shrink to a size of order 1 over Q. And the probability that the amplitude for this to happen is controlled by this distribution amplitude. So it's called a distribution amplitude, where it's a matrix element to go from the vacuum to go from one of these bilocal operator with momentum, say, xp plus and 1 minus xp plus to the, say, a pion, for example. So this is probability basically to find inside the pion a quark momentum fraction x and the other, then anti-quark with momentum fraction 1 minus x. So it's a bit like the wave function of some kind of Lycone wave function of this object. And for proton, you will need naturally 3 things: z1, z2, z3, z plus. Right? So because you have 3 partons, you need at least 3 quarks to create a proton. So twist-tree operators show up naturally in this context. They're called baryon distribution amplitude by the people in this literature. They give you a kind of wave function for shrinking the proton to 3 quarks, which can have various energy fraction, but integrated over the transverse momentum. And the general idea is that once you know this matrix element, you can calculate, if you knew these matrix elements, this distribution amplitude, you could calculate this exclusive process by multiplying this amplitude by some here 5 to 5 scattering amplitude of all these partons to deflect with each other, where they are in this Cognard configuration. Okay. By the same token, this controls the Cognard limit of the scattering amplitude. The Hamiltonian acting on this also controls multi-Cognard limits. Yeah, and of course, first prime years, as people have coming back to this topic, when you look at the dual polygon, this Cognard limit also controls what happens when you have you take a side to be null, the so-called hexagon OPE, which is the dual version of this this limit. So there's our situation in which these things appear. I wanted to mention another one on where you insert these operators at infinity. They give you you insert this operator at null infinity. They give you various things like so-called detectors. They give you various, for example, the energy flux in different directions. You can correlate it in different directions. You can measure energy to the instead of energy flux, can measure a flux of energy to the power j minus 1. Flux of E to j minus 1. So various powers of energy. Detectors. That's a long story. I would not I don't think I will go through it, but it's interesting to ask generally. So if you know the spectrum of these operators, it tells you roughly what kind of measurements you can do at infinity in terms of these energy fluxes and the correlation that can be between energy fluxes. So yeah, so there are different situations in which people have discussed those. In this case, the evolution is understood by this Brodsky-Lepage equation. That is a variant of this. But the thing which is really hard is that it's really hard to measure this wave function of the pion or the proton from experiments, because you have a lot more variables that this depend on than the variables you experimentally have access to. So that, yeah. So maybe I will stop here.
Questions? Can someone pass the mic to Rio? You just click the button on the side.
I want to know the difference between the n equals 4 and this QCD. In n equals 4, you consider this trace z del z, which is twist 2 operator.
Yeah.
And in QCD, it's like a quark.
Yeah.
But in QCD, you initially computed something like proton, and then why?
Yeah.
What's the problem or main difficulty in the real world?
Yeah. So the okay. Yeah. So the operators in QCD that you will write are different types. So there's the one with quarks, with some Wilson lines, but you also have same with gluon field strength. Things like this. Sorry, this would be there was gamma minus, but yeah, I'm messing up the indices. But you can put there's a quark distribution function, there's a gluon distribution function. They are both, and you care about both in QCD. In n equals 4, you can also do similar things with the gluons of n equals 4 or the quarks of n equals 4. But in addition, n equals 4, you also have the scalars. So that's, yeah. I would be focusing on the ones with the scalar in n equals 4. But for example, they're related by supersymmetry. So just for simplicity, in general, n equals 4, you really want to study the most general one, where you put quarks or gluons. So this is the intrinsic operator you're computing. And I think the other part of your question is like, what's the analog of the proton in n equals 4? So one thing you could imagine doing in n equals 4 is, of course, you don't have stable bound states, but you could ask about a process that is similar to this scattering we talk about. So you could take a local operator here. I don't know, it could be anything like trace phi square here. This operator, when you insert it, it decays to some stuff. And you could boost it, so it will decay to stuff that move in this direction. Then you could do the same thing here, and it will decay and it will go into this direction. And then they will hit. Say one of these Parton here will hit hard against another. The other will just move straight. And then you could measure the energy flux in some other direction. So this measurement will be controlled by the probability to find a Parton in this initial state. So this will be controlled by F, which is a matrix element of trace phi square, this likely operator, times trace phi square. So instead of putting a proton on the outside, I put trace phi square acting on a vacuum on each side. Okay, so that's the analog of a Parton distribution function. So there's a 3-point, so the 3-point coupling between local operators and these likely operators are the analog of the PDFs in n equals 4.
Thanks.
One question there. You can pass the mic down there.
Sorry, for this Hamiltonian,
Yeah.
on the 3 points that you write, for example, you take the point y in the middle.
Yes.
And okay, so for example, in the hxz, you can move z towards y.
Yeah.
Also in hyz, you can do the same configuration from both of these, from hxz and h. So you are not
Yes.
counting this configuration, or maybe you have to count it.
Yeah,
two
yeah.
times.
You need to both add them because they come with a different weight from this measure. So, for example, z here can move. So there's two ways that z can end up here. It can from hzy or hzx, and you need to add both.
Z is the middle point for.
Z here was the lattice point. Yeah. So this point Z here can move, say, here in two different ways, from HZY or from HZX. And you need to add both. Because they come from different diagrams. Yeah, so this is the complete mathematical form of this Hamiltonian. There are no restriction on this integration range.
Collier?
So in real life, Proton contains like not 3 partons, but 3, 5, whatever, right? Number. How much mass does it create if you consider all the other contributions?
See, so if you consider,
like in principle, it is a mixed state of any number of.
Yeah. So what happens is that the thing that will control this exclusive scattering at large Q is the lowest twist operators you can make. So something with, you add the 3 quarks plus an extra gluon here, will give you a 1/Q correction to this process. So this process throws away this information. This information is out there, but this process does not care.
Very good. So I think we are a little bit over time, so we can continue asking questions during coffee. So we have